Welcome to The Explainer. Today, we're going to tackle one of the most fundamental questions you can possibly ask. What is everything really made of? We're going to go on a journey from the stuff you can see and touch, all the way down to the invisible building blocks that make up the entire universe.
I mean, it's a huge question, right? The air you're breathing, the device you're watching this on, it's all matter. But, that's just a word. To really get what our world is all about, we have to see how scientists sort through all this cosmic clutter. So let's start with their first big idea. To even begin to get a handle on the universe, scientists first needed a way to organize all of its stuff. And it all starts with learning how they classify matter.
Okay, so our journey starts with the biggest category of all, matter. It's a really simple definition for, well, everything that has substance. We're talking distant stars, the dust bunnies under your bed. If it has mass and takes up space, it's in the club. This is square one for all of chemistry.
So from that giant category of matter, chemists make their first really important cut. It turns out that every single thing can be sorted into one of two basic groups, and this is the first huge step in making sense of it all. On one side, we have pure substances. So think of a bar of pure gold. It's made of nothing but gold atoms. That's it. And on the other side, we have mixtures. This is where different things are just physically jumbled together but not chemically changed. A perfect example is steel, which is basically iron with a little carbon tossed in to make it stronger.
But even inside that pure substances box, there's another level. If it's made of only one type of atom, like that gold bar, it's a simple substance, or what we call an element. But if different atoms are chemically locked together to make something totally new, it's a compound. Think about water. It's made of hydrogen and oxygen, but it's nothing like either of those gases. That chemical bond, wow, it changes everything.
So let's hop over to mixtures and see how this all builds, because this is where the world we see every single day really comes to life. Most of the stuff we run into isn't pure. All right, so some mixtures are absolute masters of disguise. They are so perfectly blended together that you can't tell the individual parts apart. These are called homogeneous mixtures, but we usually just call them solutions. When you stir sugar into your coffee, it just seems to disappear. It's still there, for sure, but it has dissolved completely into one uniform liquid. So every solution has two main players. The solvent is the big guy, the one doing the dissolving. So in our coffee, that's the water. The solute is the stuff that gets dissolved. That's the sugar. And the ratio between them, that determines how strong it is. A little sugar gives you a dilute solution, while a whole lot makes it super concentrated. But here's the twist. Not all mixtures that look uniform actually are. Some of them are just really, really good at hiding their true nature. They look like they're perfectly blended solutions, but they've got a secret. And these are called colloids. You see them every day: milk, paint, even fog. To our eyes, they look totally smooth, but the big difference is that their particles aren't really dissolved. They're just microscopic little bits of one thing, suspended and floating evenly inside another. So technically, they're heterogeneous mixtures in disguise. So how can we tell the difference? How do we expose them? Well, there's this really clever trick called the Tyndall effect. See, in a true solution, the dissolved bits are way too small to mess with light. But in a colloid, the bigger suspended particles are large enough to scatter a beam of light, making the beam visible. It's the exact same reason you can see your car's headlight beams cutting through fog. Pretty cool, right? Okay, so we've sorted matter into pure substances and mixtures, but what do they all have in common? Whether it's a pure element, a complex compound, or a tricky colloid, everything is built from the exact same set of ultimate building blocks. And here they are. Atoms. These are the fundamental particles of chemistry, and they're so small it's hard to even imagine. Like billions of them could fit on the head of a pin. Each atom has a core of protons and neutrons with a cloud of electrons zipping around it, and the number of those little guys determines what kind of atom you're looking at. But atoms rarely fly solo. Some, like the noble gases, are happy to be isolated individuals, but most of them link up with others. They can form these distinct little teams called molecules, like two oxygen atoms joining up to make the O2 we breathe. Or they can get super organized and arrange themselves into these vast, repeating geometric patterns that we call crystals, just like in a grain of salt. So just how many different types of these building blocks are there? Well, as of right now, scientists have discovered and confirmed 118 unique kinds of atoms, and we call these the chemical elements. Now, to organize all these elements, scientists created one of the most powerful tools in all of science, the periodic table. And it's not just a list, it's a map. It arranges the elements in columns called groups and rows called periods so that elements with similar behaviors all line up. This lets us predict how an element will act just by seeing where it lives on the table. It is truly a cheat sheet to the universe. And understanding this structure, the atoms and how they're all organized, lets us do something really incredible. It lets us read and write the language of chemistry itself.
Yeah, this whole system gives us a universal language for chemistry. There's this logical way of naming compounds, almost like a set of grammar rules. The most basic rule is just using simple prefixes to count how many atoms of each element are in a compound. That way, everyone's on the same page.
Just take a look at these. You can see how the chemical formula, which shows you the atoms and how many there are, translates right into a name using these prefixes. The number 2 gets the prefix di, and 3 gets tri. So for CO2, it's carbon dioxide. Makes sense, right? Once you know the code, you can read the chemical language for tons of compounds.
So let's bring it all the way back around. The next time you see a simple glass of milk, what do you really see? Well, it's not just milk. It's a colloid, an emulsion really, of fats and proteins floating in a solvent, water, which itself is a compound of hydrogen and oxygen atoms, all of which are organized perfectly right there on the periodic table. You're seeing the entire language of chemistry in a single glass.